Bernstein Sure, Con Edison Transmission, Power Market, SMRT, and Burns and Mac. And then I always kind of like to linger on this slide a little bit because so this is the $2,500 level. E2 Tech is pretty small. We've got sort of 2.5 staff who you'll meet in a second, and then a total budget of about $180,000 a year. So we've been fairly intentional about keeping things on the smaller side. That really lets us continue to do what we do. And then also TRC, VHB, and MainBiz support us around. If you'd like a free print subscription to MainBiz, and we can provide that to you as an E2 Tech member. We'll send you a link afterwards. There's a little form you got to fill out, but it does work. And they crank out a new issue every week, and they're really good. They come out promptly. So I was vlogging this event earlier. Please do join us if you can. This is tomorrow, and beer. I guess we have it on here, but 4:30. We want you there if you're going to do the energy and water efficiency tour. That does feature a tasting. So we are recording today, and I'm going to go backwards a little bit here. Get a show of hands or pipe up. Are you a member of, do you serve on one of the E2 Tech, excuse me, the MTI Tech boards? Is anybody here on one of the E2 Tech, excuse me, Maine Technology Institute Tech boards? We help facilitate these, and we're doing an event with them on the 13th. So this is for members of the MTI Tech board only, and but we really want you to come to this if you can. If you're a member of the MTI Tech board, on July 13th, it'll be on Flight Deck Brewing. It's a Wednesday. So those are the big things that I want to highlight for you today. We are always pleased to work with MTI, and if you have a new proposal, a new idea, hit that ready to start button, get in touch with us. Hit that ready to start button at maintechnology.org, get in touch with us, and we will help facilitate your project and get things going with them. So I want to give Brian Wolf an opportunity to introduce himself in a second. And I just want to check in here. I'll take my slides down. Do we have our speaker, Bill Franks? Bill, have you been able to join? So I know he was having some internet problems yesterday, so maybe there's something we can do there. Anyway, Brian, I know you have been at the Maine PUC meeting this morning, virtually tracking things down. Could you introduce yourself and tell us what you're up to?
Sure. Yeah, I'm Bryant. I'm a rising 2L at Maine Law School. So this is my first summer legal internship, working here with E2 Tech, and I'm interested in environmental and energy law. So I think I'm in the right place to kind of get to see a lot in a lot of different fields and meet a lot of people. So pretty excited to be here for this summer. It's been a good experience so far. Get to, been looking at electricity rates a lot recently. So, but it's good. It's good. Looks like Marty is off screen for a minute.
I think he might be trying to find our speaker.
I got him. There was some mix up on the date, and maybe he's at Banded Brewing right now. So is there anyone on who is a particular expert in Maine's storage goals that have recently been set? I know that's one thing that Bill touches on somewhat briefly in his presentation, but doesn't have a ton of detail. So as he's logging on, is there anybody who feels comfortable popping up and talking about that? Well, it does give me my one opportunity to make my energy storage joke, which is not a new one, but storage is like bacon. Everybody loves it and it makes everything better. So there you go.
Hi, Marty. I can jump in for a second if you want. I'm Caroline Colin and work in the energy office.
Thank you, Carolyn. Yes.
Want me to give a brief overview?
Please do. Thank you.
Sure. So yeah, in terms of the state's energy goals, so Governor Mills has been obviously working to combat climate change and advance clean energy and grow the clean energy economy and increase the renewable portfolio standard to 80% by January 2030 and goal of 100% by 2050. Also greenhouse gas emissions and carbon reduction goals. And the Maine Climate Council's 4-year climate action plan, Maine Won't Wait, which was released in December 2020, identified energy storage as a really important factor in achieving emissions reduction goals and maximizing the value of renewable energy on the grid. And then in summer of 2021, LD 528 passed, which was an act to advance energy storage in Maine, and that established the storage goals. So it's 300 megawatts of energy storage in the state by the end of 2025 and 400 megawatts by the end of 2030. And with that, Maine was the 9th US state to codify energy storage goals. The 400 megawatt goal, that represents somewhere between 17 and 20% of Maine's energy needs as of 2021. So in terms of the sides of Maine's power sector, it's pretty ambitious. And so that same legislation also directed the Energy Office to do an energy storage market assessment. We worked with E3 to do that, and that was released in March of this year. And that's available to look at on the Governor's Energy Office page. And there's also a video on YouTube that has a presentation of the consultants sort of going through the final results. That's of interest to people. We engaged over 100 stakeholders in that process, which was really helpful in kind of defining the scope and the framing. And we are hoping to sort of late summer have the energy storage forum to continue conversations about kind of policy barriers and policy development and maybe program development. So feel free to get in touch with me if you're interested in that. I can put my email in the chat, but boy, that's a helpful overview.
Thank you, Carolyn. That's great. A round of applause for Carolyn, if we may. Thank you. That was so good. And I see that Bill is here, so we'll get going with him. But I will, that really was perfect, Carolyn. So we will include a link to that E3 energy storage market assessment in our follow-up email, and also a link to the YouTube presentation that you mentioned. And so that was really perfect because Bill, and I apologize for the date mix-up. Thank you for being ready to scramble. You're set to present. You have presenter privileges and everything. So, and I mentioned that, you know, sort of the main market specifically, you didn't have, you got a great presentation, but that piece was a nice compliment. So over to you, Bill. Thank you. We're excited to dive in here.
Okay. There's my screen. Just let me get to where I can do a slideshow for you. There we go. Okay. there you are. So thank you very much. It's a pleasure to be here and get to talk to the group. So I'm going to talk to you about kinetic energy storage and other energy storage systems. And I'll talk a little bit about storage applications, energy storage technologies, then a bit about lithium-ion batteries, some discussion of how to do cost comparisons, and then I'm going to go on for a little bit about kinetic energy storage projects and specifically one project that I'm working on in New York City. So storage applications, this is a non-exhaustive list of storage applications, but storage can be used for peak shifting, for load shifting, which are two sides of the same coin, frequency regulation, ramp limitation in solar projects, if the local utility has ramp limitations that they impose on the projects, and for energy recapture. So this is a chart that shows a list of storage technologies and also the applications that they fulfill as a function of the duration of the storage facility, in other words, the amount of storage it has, and the power requirements. And the list of applications begin with pumped hydro, and I would expect that most of you know what that is. It's basically where you have two reservoirs, one above the other, and you pump water into the upper reservoir when demand is low and prices are low, and then you let it run down and run a turbine to generate electricity when demand is needed. Compressed air is somewhat similar in the sense that it's another long-term energy storage technology. Basically, it's where you have a cavern and you pump air into it and pressurize it, and then release the air to run a turbine. And often you also use gas to supplement the compressed air. One of the key issues with compressed air is, as I'm sure you all know, as you compress the air, you generate heat. And so you need to, if you can, capture that heat of compression because it improves the efficiency of the facility.
No, I like that bicycle pump analogy you used when we were going through the slides yesterday. When your bicycle pump always heats up.
Gets hot, and in terms of compressed air facilities, there are two of them currently in operation. One is in Alabama, and the other is in Germany, and I know one's under development in Ireland. Then, and maybe I'll go back to pump storage and say that there are a number of facilities around the U.S. There's one in Massachusetts. There's another in New York State that's operated by NYPA, the New York Power Authority, and then there's one on the Southern Company system, and there undoubtedly are others as well. Electrical storage are batteries, and batteries come in a number of different technologies. Sodium sulfur battery, which is a little bit longer duration. They're all defined by their chemistry. Flow batteries, lead acid batteries, which of course are the traditional battery that you have in your car to start it. Advanced lead carbon and lithium ion batteries. And I'll talk a little bit more about lithium ion in a moment. Then you have flywheels, which I'm also going to talk about, which is kinetic energy storage. And lastly, you have electrochemical capacitors. And you see that the supercapacitors have very short duration, if you look at them here in the middle of the slide, but can have quite a bit of power. Flywheels have a little bit longer duration, but still a relatively short duration. The duration goes up as you move up into other kinds of batteries, and finally up to flow batteries where you can have quite a long duration. And then pumped storage, pumped hydro, and compressed air, of course, have fairly long duration. So now a bit about lithium-ion batteries. Here are 5 or 6 different types of lithium-ion batteries, and you see they're ordered by the number of cycles you can get before the batteries begin to deteriorate. And I'm going to talk about 2, the lithium nickel magnesium cobalt oxide and the lithium iron phosphate batteries, where I'm going to show you some cost information. And basically, as you go down this list, the batteries get more expensive. This is a plot of cycle life versus depth of discharge, which is an important consideration for batteries, because if you have very shallow depths of discharge, you can get quite a large number of cycles out of them. But as you go to greater depths of discharge, the number of cycles you can get out of it diminishes quite rapidly before the battery begins to lose both power and energy storage capacity. And so that's an important consideration. If you have an application with a lot of cycles, you can accommodate that by putting in a large battery, but of course that has cost implications. And if you're going to use a high number of you're going to use a high depth of discharge, you diminish your cycle life, which means you may need to periodically replace the batteries during the lifetime of the facility. So this is some data from a recent DOE study that gives you a feeling for the cost of batteries. Now, these are the first 2, the dollars per kilowatt and the dollars per kilowatt hour, are essentially point comparisons where you're just taking the cost of the facility and dividing it by its capacity. And this is for a 10 megawatt 4-hour battery, is the example that I've selected. And it also has an estimate of costs both in 2020, more or less current, and 2030. And you can see that the prices are expected to continue to go down. And then the last column is the levelized cost of energy, which gives you more of a lifetime cost of the battery. One issue with batteries is they can catch on fire, and usually the fires come about either because, well, they're all some version of human error. Either there's a flaw in the battery management system, or there was a manufacturing flaw in the battery, or somebody who has access to the facility did something to cause a short. And so it's very important when you install a battery facility is that your local first responders, the fire department, understand how to address the battery, because there was an incident in Arizona where the battery caught fire and the fire department came up and they opened the door on the facility, which allowed air to enter and caused quite a significant explosion, which fortunately nobody was killed, but a number of the firefighters were injured. When you're comparing the economics, especially if you're comparing a short duration, high cycle facility like kinetic energy storage with a longer duration, lower cycle life facility, you need to do a lifetime comparison. So you take into account replacements if they're required. And the way you do it is you compute the lifetime throughput of energy in kilowatt hours. And then you divide the lifetime capital costs and operating costs by the throughput, and that gives you $1 per kilowatt hour comparison. And the lifetime throughput is just the average depth of discharge times the storage capacity times the number of cycles that the facility sees. So moving on to kinetic power systems. For full disclosure, I'm a representative of Beacon Power, so I have a lot of familiarity with their technology, and I help them implement projects using this technology. Beacon's been around now for over 20 years. They have a factory in Teamsboro, Mass, which is quite close to us here. 20 megawatts of Beacon flywheels have been operating in Stephentown, New York in a frequency regulation mode since 2011. And another 20 megawatts has been operating in Hazel Township, Pennsylvania since 2014, 2015. So there are more than 400 systems, 400 flywheels that are currently being maintained by Beacon under contract for clients. And this is aggregated over 3,800 years of flywheel operating time. There's a lot of experience accumulated in operating flywheels. And you can see some photographs of the manufacturing facility here. This shows the vacuum containers and some of the rims. This is a device for balancing the rims. And this is just a photograph of the assembly facility. So this is a Beacon Series 400 flywheel. The blue is a vacuum container. And the black is a patented composite rim. It's a fiberglass composite. And it spins at 15,500 RPM, so quite fast is its top speed, down to 4,000 RPM, which is the lower cutoff. So 15,500 RPM defines when it's full and 4,000 when it's empty. The flywheel is supported by a magnetic lift system. So it's spinning in a vacuum, supported by magnetic bearings. It has an aluminum hub, which is this yellow here, which connects the rim to the shaft. And it has a steel forging in the shaft, which keeps everything in line. And then there's a brushless magnetic motor that converts electricity into mechanical energy, or vice versa when you want to discharge the flywheel. Flywheel comes in with two different motors at the moment. You can get a motor that is nominally 100 kilowatts. It's actually rated at 200 kilowatts. And so you can get, at 100 kilowatts, you have 15 minutes of storage, or 25 kilowatt hours. But you can operate the motor at a higher power. You get shorter duration, but higher power out of it. So for instance, in a project I'm going to discuss shortly, we're using 6 of these rated at 167 kilowatts to give us a 1 megawatt facility. This shows you how the flywheel is actually installed. It's installed below grade in a concrete foundation. And then above it, you have a power control module and a cooling module. And this shows you what a 2 flywheel facility looks like. This is a photograph of a facility in Ireland. So the flywheels, this is the top of the flywheels, and they're concrete containers in blue. These are the power control modules. This is the cooling system. And this is a photograph of the manufacturing facility. This is a photograph of Stephentown. It shows you the 200 flywheels in Stephentown. And this is an artist's rendering of Hazel Township. And you can see that in the Stephentown facility and the Hazel Township facility, you have 5 flywheels on each side of a container. And all the cooling and power control apparatus is contained inside this container. And so you put 10 of these modules together and you have a megawatt, or 20 of them and you have 20 megawatts, 10 megawatts, excuse me. And the design has evolved since then to that of the one that I showed you here, with the power control module housed in a separate box. And this is what a 20 megawatt facility would look like if you use the more modern, more recent technology. So now I'm going to talk a little bit about subway regen braking. So what is regen braking? Well, when the subways, in this case, we're talking specifically about New York City Transit, when they brake, they first use their motors to brake. So the motors basically are operated as generators, which slows the train down till they get about 5 miles an hour. And then they use mechanical brakes. And nominally, this electricity that is generated by the motors during braking just goes to onboard resistors and is dissipated as heat, which is one of the reasons that the subway is so hot in the summer. But the use of a motor in this way is similar to the design of an electric or a hybrid motor vehicle. And by using this, we can save up to 30% of the energy consumed by the subway. So this is a photograph of the site. One of the biggest challenges in a place like New York City is identifying sites. So this is a site in the vicinity of 61st Street in Woodbridge on the number 7 line in Queens. So there are 3 main outcomes of this, and a single installation like this 1 megawatt one that we're planning, which is the result of a $1 million grant that I obtained from NYISO. It will save the Metropolitan Transportation Authority between $300,000 a year and $600,000 a year, depending upon exactly how you operate it. So this represents about a 30% reduction in the cost of the electricities used by the subway. And if these were installed throughout New York City Transit, they would save New York City Transit about $100 million a year. Reduced reliance on energy from the grid also translates into reduced emissions attributable to the operation of the subway. And it also translates into improved passenger safety, because with the energy stored in the flywheel, in the event of a power outage on the New York City Transit system, you can actually move trains back into the station and discharge your passengers safely. So the Beacon 400 has a whole series of safety features. First is that it's installed below grade, and then is a whole array of monitoring and safe shutdown for out of specification parameters. So bearings, the motor, the power electronics, the coolant, and the control cabinet are all monitored for temperature. Any indication of vibration indicates the onset of a crack, which would cause the flywheel to be shut down. There's a redundant overspeed shutdown. There's a measurement of the magnetic bearing state of health. Current and voltage limits are monitored to protect components. Turbo pump power is monitored, which indicates the onset of a vacuum leak if there is one. Similarly, vacuum pressure is monitored, and the coolant flow to the coolant pump is monitored. And the flywheel consists of a self-provided uninterrupted power supply, because if outside power is lost, it can just coast down, powering itself with its own internally contained power. And last but not least, there's a dust control system, which prevents the dust explosion in the likely event that the flywheel wobbles and abrades against the containment. So the next step for this project is to complete the engineering review of the site, finalize a hosting agreement with New York City Transit, including the terms for them to purchase it, permit the site and the project, And we would expect to install the equipment over the next 18 months or so. So now I'm open for questions.
Good work, Bill. A really interesting discussion. Yeah, take down that share and we'll get things going a little bit with a really engaging Q&A. This is a really amazing looking project, and excited to get into more discussion. So what I like to do at this point is ask you to turn your camera on. We're going to do a little smiling screenshot as Bill's taking those slides down, and that's a way to get you kind of engaged, because part of what we try to do with these is simulate that hallway discussion that we would have at a live event, and it's meant to be sort of informal. So let me see, Bill. I think the bottom there, maybe there's like stop sharing thing, or maybe at the top.
I do stop share, yeah.
Yeah.
Okay, I got it.
Okay. So I'm going to put all of you in the old gallery view here. And if you're in the mood and you want to turn on your camera for me, and on the count of 3, we'll do a little smile. And for the questions, I think it's great if you want to pop up and introduce yourself and your company to get a little interactivity. If you don't want to do that, that's totally okay too. You're grabbing lunch and so forth. So anyway, on 3, a good smile if you don't mind. 1, 2, 3. All right, I got you. What a great group. So Aaron from Nile Water Heating Systems, are you handy there? Because I know I thought you had a great question that we could start off with.
Sure. I was curious why they were installed underground, but I think he actually answered that. I believe it's a safety mechanism in case that everything goes haywire. Is that correct, Bill?
That's correct. You have a lot of energy. You know, the flywheel, when it's operating, it has an energy that's equivalent to a cement truck going about 60 miles an hour. So you want to contain that energy if, I should say, something goes haywire.
I know that I read an article about a flywheel manufacturer in Utah. This is well over 20 years ago, and that was one of their main challenges, was how to build something that was safe, but also not so overbuilt as to be ridiculous. So that's an interesting way to solve that. It's great.
Yeah, really good question. Thank you. I'm going to go in order that I saw some in the chat, and then we can kind of keep going with them too. And Bill, this goes back to a slide that you showed, so we might ask you to put it back on the screen. You know, the slide that showed pumped hydro and batteries and so forth. Catherine, are you with us? You want to ask about the hydrogen?
Yeah, thanks. This is so interesting. Great presentation. Yeah, my question was, would you consider hydrogen something to put on that slide? And if so, where would you slot it in?
Well, hydrogen is generally considered long-term storage, so it would be it's slotted in on the right-hand side of the slide, and also has fairly high capacity. So in the upper left-hand corner, very similar to pump storage or compressed air.
Got it. Thanks.
That's a great segue. I think we had a question from David about the location of the pumped storage facilities. Did you say there was one in Massachusetts somewhere? Did I get that right, Bill?
There is one in Massachusetts, but I couldn't tell you specifically where. I know if you follow New England, ISO New England, and read their reports, occasionally the reference to that pump storage facility comes up.
It's in Western Massachusetts, Bear Swamp.
Thank you.
There's a couple of them actually. Yeah.
Near a swamp, huh?
Well, I think they call it Bear, so I don't know why they call it that.
Oh, Bear Swamp. Okay, yeah. All right. David, you had a question about the caverns. The question that was above my pay grade. Want to go ahead and ask it, David?
I was just curious as to the size of the compressed air caverns, for example, the one you mentioned in Alabama.
I actually don't know its volume, but I think they are fairly large.
Are these in salt domes?
Salt domes are one of the places, and I believe the one in Alabama is in a salt dome. Salt dome is one of the places that they put them. They were evaluating a facility in upstate New York where they were going to actually put it in a naturally occurring cave in limestone, I believe. But that one never came to pass.
Great.
That's
Thanks.
really interesting. I'll kind of go in reverse order here on some I'm seeing in the chat. Arthur has got a good question about size limitations. You want to go ahead and ask that, Arthur?
Sure. My language is failing me, but I guess what I'm trying to say is, when is it too small or too big for this type of storage to be used from a cost perspective, taking into account that obviously you don't have, I mean, current storage doesn't always account for sustainability costs that are hidden, i.e., batteries have to be recycled or are destroying pieces of Africa, and this might not. So when does it make sense to get a flywheel for size?
Well, applications that are good for flywheels are frequency regulation, as I showed, where a 20 megawatt or similar facility is about the right size. And I know that there's consideration of installing an additional facility in the PJM market. Flywheels for microgrids is a very important application, which I didn't mention in my presentation. But flywheels have a very fast response time, less than a millisecond. And they also have the capability to perform both the grid forming as well as the grid following function. So in a microgrid, especially one where you have maybe diesel engines as a longer term source of power, flywheels are very good in helping you separate from the primary grid and reconnect to it because of their very fast response time. And then when operating in an island mode, they have this grid forming function, so they can operate the microgrid in that fashion.
It's an excellent topic area, microgrids. We should dive into that a little bit, maybe in our discussion here. We've got a grade of some really good questions that are coming in. Lifespan, and also I know Aaron from NYISO is their company's very good at recovering waste heat. Is there any waste heat? So you want to take lifespan first, Bill, and then waste heat?
Sure. Flywheels have their utility grade technology. So they have a 25-year life, and you can cycle them continuously during that 25-year life. So they have an unlimited number of full charge discharge cycles.
And do they make heat?
They do not. So you're operating in a vacuum. So one of the issues in designing the motor is designing a motor that has very little eddy currents in it, because if you generate heat in the motor, you have the only mechanism you have for removing heat is radiation, because you're in a vacuum. And so flywheels do not generate heat, and nor do they generate noise. When one is operating, you can stand next to it and you don't realize that there's something spinning there at 15,500 revolutions per minute right next to you. Absolutely silent.
That's really interesting, and that's eddy current obviously is used to separate out types of metals and so forth, and I wouldn't have guessed that was part of this. Brian has an interesting question about the regen braking. Brian, do you want to ask that? Okay, gotcha, Brian from RLC. I see the fireworks.
I'm sorry, I was talking into a muted mic.
No worries.
Yes, so you mentioned with this subway application, saving 30% of the energy by absorbing the braking energy and then reusing it in a flywheel. And you actually mentioned the analogy to regenerative braking in an automobile, where it's converted back into electricity. I was wondering if that was an option for the subways as well, if they could regenerate their braking energy into the third rail to reduce their net energy consumption, similarly to that 30%.
They do. There's something called the cutoff voltage. So the energy from the regen braking in the subway car is injected into the third rail. And if there are other cars in the vicinity, they can use it up until you get to a certain level, which is 720 volts on the New York City transit system. And above that, it goes into the resistors, as I described. But if you have the flywheels on the system, then you can continue to absorb that energy. And in fact, it's, the energy is absorbed into the flywheels, and then the flywheels inject the energy again into the third rail to accelerate the train out of the station.
Yeah. Yeah, very interesting.
Super.
Just
Go ahead, Brian.
just a follow-up note, we were talking about the flywheels we saw on the screen were half buried because they're rotating so fast and there's so much inertia there. On a train, you don't have that capability, and you introduce a lot more vibration and whatnot.
Well, the flywheels are not actually mounted on the train. The flywheels are installed on the wayside and connected to the third rail. So they interact with the train through the third rail.
Okay, I misunderstood. Yeah, that's a great idea. Thank you.
This is really interesting, and we're getting into the power hour phase here, where the questions always get better as we go, and they are continuing to. There is a question from Susan Cavino, and Susan, do you want to ask about this? And I have an add-on to your question too that might be interesting. And after that, we'll go to Christian.
Yeah,
So,
I was just curious about whether or not Mr. Franks was familiar with a mechanical type of storage being developed down in Texas using the 1 mile deep casings of inactive gas and oil wells to drop a 10,000 pound weight. And there are, of course, thousands and thousands of inactive wells in Texas. And the win-win is that it stands ready to deliver power quickly, depending on how many you deploy at one time. But it also provides a revenue stream from the electricity market that can be used to actually cap those inactive wells that may be leaking methane into the atmosphere.
Yeah, I can't say that I'm familiar with that particular technology, but there are a number of variations on it. Out in California, there's a company that's actually using rail cars where they, run them up a hill and then let them roll down to generate energy. So, and there are also other technologies which are not kinetic energy technologies, but one we haven't talked about is thermal energy storage. And so there are companies, there's actually a project in New York at a defunct power plant, where what you do is you take an old coal plant that you don't want to operate any longer, and you have the generator and the turbine there, and you have the interconnection infrastructure, and then you take concrete blocks and heat them electrically off peak when prices are low, and then for peaking you can use them to generate steam to run the turbine and generate power. And so it's a use for for old coal plants, so that you don't have to decommission them. You can continue to use the interconnection portion and the turbine portion and get some value out of that.
I should know that we have an E2 Tech member, Peregrine Turbine Technologies. I'm going to put their link there. Some of you may know David Stapp, that was one of the principals. They're based in Wiscasset, peregrineturbine.com, who is working on a variation on that, a thermal storage for islanded or somebody help me with the lingo, excess energy generated that can't find its way onto the grid. But I want to highlight something I just put in the chat. The genesis for this discussion, actually, Susan, is a really interesting New Yorker article, and I think the link I shared will let you, isn't paywall. I'm not 100% sure of that, but of all the different types of energy storage that's out there, including a project that is makes cement blocks and stacks them and lets them slide back down, and all kinds of interesting technologies. I do like, I mean, Bill is presenting a technology that is running today and has, which is pretty neat. So I think that's amazing. Christian, I think you had your hand up. Pop up with a question.
Yeah, just a bit of regenerative trivia. I believe the Milwaukee Railway, Milwaukee, St. Paul, Chicago Railway. I should get that right. My grandfather was the chief electrical engineer for that electrification. They did regenerative braking in the 1920s and over the Rocky Mountains, whereby trains coming down one side fed their braking energy into the catenary wire overhead and helped the trains climb up the other side, saving about, so I heard, 12% on their electric costs, but a long time ago. Pity the railway went out of business. Thank you.
Oh, that's really interesting. Yeah, storage economics, when the economics work, then these things happen. Jay, you've asked a good question about economics. Do you want to pose that? You're certainly welcome to pipe up.
Sure.
Thanks.
Sure. Bill, thanks for your presentation. Jay Brandeis, my question's about, how we look at storage. I mean, we compare generation typically on a dollar per megawatt basis. And I noticed you showed economics focused just on dollar per megawatt hour or LCOE. At what point, or do we ever really compare storage technologies on a dollar per megawatt basis?
Well, you can always do a dollar per megawatt calculation. And I don't think, as I said, that's just one point of information. For instance, if you compare a flywheel on a dollar per megawatt basis with a battery on a dollar per megawatt basis, you're really comparing apples to oranges. So that's why, as I said earlier, you need to do a lifetime cost comparison. And the parameter that I use for that is the lifetime throughput in kilowatt hours. The absolute value of the energy going in and out of the storage facility. And that gives you a real apples to apples comparison of both the capital cost, for instance, if you're comparing a battery and have to replace it at some point during the lifetime of the facility, with the flywheel.
Okay, thank you.
That's really
Mark, and something else, reverting back to the discussion of thermal energy storage. The name of the company that's making those concrete blocks and is proposing to install them at defunct coal stations. The name of that company is Storeworks, and they have a demonstration facility with the Southern Company, and I think they're working on developing another one in California at the moment.
That's incredibly interesting. I know it's attracting major venture investment. We'll include that Storeworks link, and if you check out that New Yorker article, we'll include that link too. It's somewhat irreverent, but is really informative as well. Eric, do you want to? That's a great question about beacon flywheels. Do you want to pop up and ask that? putting you on the spot. There you are.
No, it's fine. I've had some experience with flywheels. And an early question and problem was the high cost of carbon fiber, which is a wonderful material and exactly appropriate for this application. And in fact, the carbon fiber manufacturer, Toray, spent a lot of time and energy trying to help bump start the flywheel technology business. But the cost of carbon fiber was a significant problem for the early developers and a barrier to entry. And I'm wondering if carbon fiber has come down since then. That's, the high cost of fiber is old news.
Yeah. Well, first of all, it is Toray carbon fiber that's being used in the Beacon flywheels. And I think the costs have come down, but I don't have any numbers at my fingertips. But important thing to remember is that the amount of energy stored goes up as the square of the speed of rotation of the flywheel, and that's why carbon fiber is so useful, because you can get much higher speeds than you can with steel or metal, and the cost per kilowatt hour stored is lower using carbon fiber than it is if you made a steel flywheel, for instance.
For sure. Yeah.
Yeah, it's super interesting. Okay, the last question goes to Don Parent. I have motivation in giving Don the floor too for this last question, because we haven't got it on the calendar yet, but Don is going to be giving our next one of these E2 Tech Connects on some failure analysis in energy projects. I think it's going to be a really good one, so watch your inbox for that. But Don, I know you have a question for Bill.
Yeah, thank you, Marty. I appreciate that. And I actually remembered to unmute my microphone, so that's probably a first. So my question, I guess, was really cost per kilowatt hour and how it might compare to, say, something like a lithium-ion battery. Is it for, say, large-scale storage? It seems like a lot of people are working on large-scale storage using batteries. I certainly know the military is doing that. How would it compare? Why would they want to use one over the other? Although it sounds like lifetime is one of the reasons, but can you elaborate on that, please?
I can elaborate, and if Marty will let me share my screen again, I think.
It certainly may.
Well, I thought I had a figure ready to go, but I don't.
Okay.
Sorry about that. I was looking at it earlier today. Anyway, the as you go up in cycles, the cost of a flywheel is relatively level, and as you go up in cycles, the cost of excuse me, as you go up, cost of a flywheel is relatively level, and the cost of the batteries increase as you go up in cycle life. So I don't know whether that answers your question, but and if you're interested, I can dig up that chart and send it to Marty, and he can pass it on to you.
We will do that.
Well, I was going to simply ask on a follow-up. Would it? Are they relatively maintenance-free during that period? Do you have to change the oil? I guess, what do you have to do to them over that 20-year lifespan?
You don't have to do a lot. In fact, the turbopumps wear out, so you have to change the turbopumps. Right. And you have to check the electrical connections for, because the thermal expansion, and so you have to check the electrical connections. And that's about it. So the maintenance is relatively low, and the flywheels just, as long as you keep everything else, keep all the electronics working, the flywheels just sit there and spin because they're spinning in a vacuum supported on magnetic bearings.
Excellent. Oh, that's kind of how I feel sometimes. Anyway, sometimes we move things ahead like we did with this presentation today. So really great. Please join us tomorrow. This is going to be a fun event, and none of these things happen without our great sponsors, and particularly without Riley's backing. Riley, thank you so much for pulling all these forums together. So we hope to see you tomorrow night at Banded. We've got a couple more of these coming together, E2 Tech Next. Actually, we're looking for ideas too, if you would like to present. And so Carolyn Colin from the Governor's Energy Office, thank you so much for stepping in. We appreciated that. We'll include all the links and the recording. And Bill, great presentation, excellent discussion. Huge thanks on behalf of E2 Tech. We'll get the slides and recording out. And with that, I will wish you a wonderful afternoon. I know many of us are at the Offshore Wind Energy Markets Assessment. So if you're going to that, I will see you over there.
Okay,
Take
thank
care
you
and have
very
a
much,
nice
Marty.
afternoon.
And I'll put in a plug for Bandit. I had dinner there last night, so it's very good.
Aha. Okay. Well, there you go. All right. We'll hope to see you there, and take care. Bye.
Bye-bye.